So today I'm going to sort of follow on from where we left off on Tuesday, and where Tuesday was a bit more. Do you want the microphone? Where Tuesday was much more of a didactic lecture. I'm going to focus a little bit more on some of the research we've been doing. Some of this is published. The first half is, the second half isn't. But I think it's sort of it's a nice way to bring all the sort of information that we've been talking about before, and the details of cerebellar processing. It's actually on.
Did you do something here?
It's on mic. That's it. So yeah, we're going to look at specifically at the input layer of the cerebellum, and we're doing all these experiments in vivo using patch clamp electrophysiology, but just having a look at how inhibition and different modes of inhibition actually shape the sensory responses that granule cells evoke or can be evoked in granule cells, and how this propagates down to downstream neurons in the cerebellum. So just as a little bit of a recap, just to focus in on what's the sort of important aspects of what we're talking about. Again, this is what I showed on Tuesday in terms of the 5 cell types that are present in the cerebellum. And what we're going to focus on today is basically processing in the input layer, or the granular layer, or the granule cell layer. As I mentioned before, that granule cells are the most abundant cell type in the brain. So I think in a human there's 1 billion granule cells. So we're really trying to understand, okay, and I hope from last lecture you sort of understood that the cerebellum is a relatively simple structure in terms of there's 5 main cell types. It's crystalline structure. You look all over the cerebellum, and it's pretty much the same sort of orientation and setup of the different cells, and it's a relatively just a feed-forward circuit where information comes in, it gets processed, and then it leaves the cerebellum again. But I think try to highlight the fact that the complexity in the cerebellum, or at least in the granule cell there, comes from the fact that it receives information, auditory information, vestibular information, visual information, motor information, a huge variety of different types of information that integrates in this layer to then choose what sort of sensory responses, or at least evoked responses, are then propagated to the downstream layers in the molecular layer, and ultimately out through the cerebellum. So what we're going to focus on today is the sort of integrated properties of granule cells, and how excitation drives the granule cell, and more importantly, how inhibition from Golgi cells, which is the granule cell layer inhibits into neuron, how inhibition and multiple modes of inhibition actually regulate or shape the responses that the granule cell produces, that then ascends up into the molecular layer and propagates along the parallel fibers, which ultimately synapse with the Purkinje cell. This will then regulate Purkinje cell output, which then leaves the cerebral cortex. So we're just going to focus in on the integrative properties of the granule cell. And again, just as a little bit of recap, why there's a sort of difference. It'll become important in terms of one of the types of inhibition that we're going to look at later. That the glomerulus is a rather unique structure, and as I said before, that it's got this glial sheath which covers, here's a mossy fiber terminal, which is glutamatergic, releases glutamate onto the dendrites of between what we talked about 20 or 50 different granule cells, so you get this cluster activation, and you get the inhibition coming from the axons from the Golgi cells, which are shown here in yellow, which provides the inhibitory input. But this whole structure has this glial sheath that covers all the dendrites and the mossy fiber axon terminal, and sort of encapsulates or at least contains all the released transmitter that is released from these from both the mossy fiber terminal, and importantly for this talk, sort of contains the GABA that's released from the axons from Golgi cells, and this will become apparent why that's quite important later on. So this is where all the synaptic input comes into granule cells, and again, as I said before, they've got 3, 4 on average dendrites. They're really quite short. They're only maybe about 10 microns, and all the synaptic input, well, let's say the majority of the synaptic input comes in on these little end feet. let's say the majority of the drive or the excitation of inhibition comes onto these little end feet or claws of the granule cell. So what we're going to, in the first part of the talk, I'm going to talk about work that myself and Mickey did back in London on the role of tonic inhibition. What I mean by tonic is this persistent GABAergic inhibition that's present in granule cells. And these are mediated, we talked about this before, by these extrasynaptic or perisynaptic receptors, which have got an extremely high affinity for GABA. So they sense the ambient levels of GABA in the extracellular space, which is about anything between about 100 and 200 nanomolar, so really high affinity. And when they're activated, they just sort of flicker on and flicker off, and they're persistently active, or there's at least a persistent presence of GABA that can activate them. And what you see when they're activated, or when you block them with a selective GABA receptor antagonist, you see that you block this standing tonic inhibitory conductance, and to a certain extent you're blocking fast phasic inhibition, which these are fast iPSCs here, but this is the important one in terms of tonic. In the second half of the talk, after a short break, we'll talk more about, so this tonic is, there's a debate in the field as to where tonic, or the GABA that mediates this tonic inhibition actually comes from. And there's been a debate that's been raging for probably 10, 15 years. So some people say that tonic inhibition comes from spill out of GABA that is released from the inhibitory interneurons or the Golgi cells. So just given time, there's a little bit of GABA that comes out, and it sort of dissipates in the extracellular space and leaves this low nanomolar concentration of GABA. So basically people have said, okay, if we block Golgi cell release by putting on tetrodotoxin or other blockers of release, do we see a change in the level of tonic inhibition? Some people, yes, they have seen that, but it seems to be very age dependent. And the reason for that, we don't know. There's other people in the field or other studies in the field that seem to suggest that the tonic inhibition comes from release from glia or release from the reversal of transporters that is distant from the site of activation. So it's not entirely clear as to where the GABA mediates this tonic inhibition comes from, but it's there and in low nanomolar concentration in the extracellular space, and in almost all granule cells you can see this tonic inhibitory conductance. So we'll talk about this now, tonic inhibition in the first half, and then we'll go into the more direct phasic and spillover inhibition, which comes from direct release of GABA from the Golgi cell terminal, which is activating receptors which are directly opposed to that interneuron axon terminal. So the main question that we went after for a start is we know that granule cells get these multiple modes of inhibition, but the main question is why? Why does this sort of relatively simple cell actually require to have 3 different modes of inhibition? What does it actually do in terms of sensory information processing? So to tackle these questions, we switched to using patch clamp electrophysiology in the intact brain, so that we could go down and record from these relatively small cells. But what we wanted to do was be able to look, so there's been several decades of work looking at these different modes of inhibition in granule cells in slice preparation. So they either block one type of inhibition, or they stimulate the release, and have a look at what it means in terms of the sort of spike output that the granule cells can actually produce. But what we wanted to do was actually use intact brain, intact system, and then use a sensory stimulus that will actually be important to actually trigger granule cell activation, and then have a look at perturbing or interfering with the different modes of inhibition to see how that actually changes the shape of the sensory response. So I mean, that's one really strong advantage if you want to look at how cells are actually processing the synaptic input to generate meaningful behaviorally relevant spike output patterns. I mean, all the work I'm going to show you today is work that we did under anesthesia, but all the work that I do in the lab, similar to what Mickey does, is we're transferring the same sort of technology, but doing it in awake behaving animals. So then you can actually, instead of with an anesthetic prep, obviously you've got to give it some form of stimulus. So we're giving ear puffs to the whisker whisker for somatosensation, but with a weak behaving animal, then you've got the ability to actually engage it in a specific task or in a specific behavior, and then you can look sort of real time how sensory processing or information processing occurs. So it's a really, really powerful technique to be able to do that. And over the past 5-6 years, ourselves and a lot of other groups have really tried to tweak the technique to get as close to the type of recordings that we can get in slice, but being able to do it in vivo, in the intact system. We're not there yet, but we're getting pretty close. And I mean, for the aficionados, in terms of access resistance, that's the main access resistance, or the continuity you have of your electrode to the actual cell is the main problem. And some of the early recordings that were done in vivo, they would be using access resistances of 50, 60, 70, 80 megohms. And there's an argument that, in a slice preparation, you're using 10 megohm access resistances or less. So you've got really good electrical continuity with the cell. When you start going beyond 50, 60, 70, the argument could be why you're not using shards. Because really the type of information that you're going to be acquiring is really heavily filtered. You're not really going to get the sort of resolution that you can get in slice preparation. So that's where you have to ask the question is, what type of information do you want to acquire? And what level of precision do you want to acquire that at? Because this is an amazing technique, but also it only gives you the information about a single cell. So what type of technique do you want to apply to be able to answer the specific question that you have? This is great. At the present, it's a sort of sexy technique. It's given us an amazing amount of information, but it is limited in its ability to give you all the information you might need to understand a neural network. So we want to use patch clamp electrophysiology. All the data I'm going to show you today is from an area called CRUS2, which is out in the cerebellar hemisphere. But by basically just using normal patch electrodes, we're just under high pressure, doing a craniotomy for a start. We do a gyrotomy, so we actually expose the cortical surface. Then we're just using normal patch electrodes, 5-7 megohms, under high pressure, maybe 200 millibars, just to keep the tip clean. Go onto the cortical surface, and then we drive down to the depth that we want. So in terms of, this was all done in juvenile rats, so we're going down to about 400 to 600 microns under the surface. Then we reduce the pressure, and then we go to what we class as searching pressure. This can be seen in the next slide, where all we're doing is monitoring a test pulse. So we just send a test pulse through the patch pipette, and we're monitoring the amplitude of the test pulse. Once we get down to that 400-600 microns under the surface, then we just take 2 micron steps forward in a blind configuration, so we're not visualizing anything. And we just 2 micron steps as you progress through, and then when the electrode comes in close apposition to the cell, obviously the resistance is going to increase. The test pulse decreases in size, and we classify that as a hit. And then we'll take maybe two micron steps to really impinge on the membrane of the cell. Resistance is going higher each time, and then we know we're next to a solid structure, which is probably a cell membrane. And then we vent to atmospheric pressure, and the membrane then comes back onto the patch pipette, and we can form a cell-attached recording, which in itself is a good recording configuration, because we can, without perturbing the actual interior of the cell, we can then monitor the spike output if we give a sensory stimulus. Or most of the work that we're doing, then we just give a brief negative pulse breakthrough to the whole cell configuration, then we have electrical continuity of the cell where we can manipulate the membrane potential, or can monitor both input to the cell or the output. So all the work that we're going to be talking about today is with the blind patch technique and the whole cell. As I said, we're recording from CRUS2, which is an area I briefly mentioned on Tuesday. It's a really strong, it's a fractured somatotopic map. It gets a really strong input from, or somatosensory input from different areas on the face. So different areas of CRUS2 and CRUS1 get input from the whiskers, the upper lip area, the ears, the face, but it basically is a topographical map covering the entire of the face. But the stimulation we're doing is just giving a brief 60 millisecond ear prop to the whiskers and the upper lip area, which is seen here, and we're recording from in this sort of area here. And in general, given a little bit of movement of the ear puff, which is quite focused, we can find or at least map the receptive field of that particular granule cell. And once you do find the center of that receptive field, you get a pretty strong, reproducible, faithful response. So that's quite nice, because that's exactly what we're looking for, is because we want to manipulate the inhibition that's coming to these cells, we want a really faithful, reproducible sensory response, because then once you manipulate it, at least you can say, okay, that's a direct result of the manipulation that we were sort of putting on the system.
Possibly a stupid question. How do you know the cell is a granule cell, the one that you make?
So from a physiological point of view, they have got in terms of capacitance, it's only maybe 1 or 2 picofarad, so really small cells, extremely high input resistance, so it's almost up at a gigohm. And the simple answer, which will cover any of the experiments you want to do in vivo, is recover that cell. Yeah. So that's a. Yeah, that's the only way of doing it, and it's, yeah, so that's a recovered granule cell. I mean, it's not super easy to do, but if you focus in on the protocol and the way that you're actually doing it, you can get up to about anywhere between 60 and 80% recovery rates. So for the motor cortex stuff I'm going to be showing later on this afternoon, then we're up at about 80% recovery rates, because we really need to know. And it's an interesting point as well, because when you start pushing a big bit of glass into the brain to a certain extent moves with the glass. So when you go, okay, I'm 400, 600 microns under the field surface, are you? Is the first question. Because if you're just pushing the brain down as you go, it may look like it's 400, but you're actually 250. So it's a really important point that actually I would stress to anyone who's doing this, try and recover every cell that you possibly can, to really know that you are at the depth and recording from those cell types that you say you are.
But in this case, it's like a shell that is like 7 microns in diameter. And there are billions of them. So go and find it, you know.
Yeah.
So it's like it would be just a tiny blip of like black spot over the brain, and you have to find out where it was.
But to take that to a different level, we also published a paper on recording from mossy fiber terminals. So I showed a little bit of data at the other lecture about we actually patched onto the mossy fiber terminal, which is only maybe 5 microns across. Again, blind patch technique, so it's kind of by random, but we could get stable recordings of that. But what we managed to do was fill those mossy fiber terminals. So if you think trying to find one granule cell is tough, try and find a single axon within the intact brain. That's really tough, but you can do it. So it's just this painstaking searching through the brain. Okay, so tonic inhibition. That's the first part that we'll sort of talk about. What do we think that tonic inhibition is actually doing, and why is it there? So as I said, it's this standing tonic inhibitory conductance. You'll find in every single granule cell that you're recording, whether it be in slice or whether it's in vivo. You'll still see it because there's still an ambient level of glutamate within a slice. There's a huge body of work looking at what tonic inhibition actually does in slice. And from the work done in vitro preparations, it's sort of accepted at least that tonic inhibition is generally setting the excitability of granule cells. So if you look at control, and this is in slice from a current clamp recording, where you're basically just putting in steps, hyperpolarizing, depolarizing steps to look at the excitability of the granule cell. This is in control, so you see up at the sort of the maximum steady state current injection, you get a number of spikes at a certain frequency, and then if you, using the selective GABA receptor antagonist, which is SR, or gabazine it's called, when you block GABA receptors or block tonic inhibition, then what you find is that much smaller, the cell becomes much more electrically compact. You block the inhibitions in there, it's much more electrically excitable, so when you give much smaller steady state current injections, you start to get more and more and more spikes out, so the electrical excitability of that cell is actually enhanced. So it's been known for a number of years that tonic inhibition is sort of setting or regulating the level of excitability of granule cells. But it wasn't really known whether it was present in vivo and what it was actually doing in terms of sensory information processing. So that's the experimental setup we've got. We're just using patch electrodes, patching onto granule cells, and using our air puff. And then, in terms of what I was talking about before, pharmacology is relatively difficult. Most of the work I'm going to show you today is by applying pharmacological techniques. And what we do is we basically just put a diffusion or just physically applying it to the open craniotomy, which is itself tricky to actually do because if you get movement of the solution that's sitting on top of the brain and your electrode, this is only a 5 to 8 micron cell, so any movement of your electrode sort of reduces the integrity of the seal and you lose your recording. But we're topically applying gabazine, so a selective GABA antagonist. You leave it on the cerebellum maybe about 5-7 minutes to diffuse down. It slowly diffuses down from the surface and then blocks all GABA receptors. And when we do this, if we look in control, so this is a voltage clamp recording, and we're holding the cell at 0 millivolts, so it's the reversal potential for excitation. So here, all we're seeing is inhibition. So these outward currents that you can see here are phasic inputs from Golgi cells. This is phasic iPSCs. Then when we apply the GABA receptor antagonist, blocks all GABA receptors in granule cells. Obviously, you're going to block these fast phasic iPSCs, but also what you see is a shift in the holding current, which is indicative of blocking the standing tonic inhibitory conductance. So this is a good indication that we do indeed, also in vivo, which is, as you predict, that we do have tonic inhibition in granule cells. So we know that tonic inhibition is actually there, but if we sort of block this tonic inhibition, what does it mean in terms of sensory evoked spike output in the granule cell? So we've switched to current clamp here, so we're just monitoring trajectory of voltage in the cell, and here's in control. We apply our 60 millisecond air puff, so a brief air puff to the whiskers in the upper lip area, and you get a number of EPSPs that summate until it reaches threshold, and then on average you get a burst of 3 spikes. And this is pretty, as I said, it's pretty faithful and reproducible. Each time you give the same sensory stimulus to the same granule cell, on average you'll get 3 spikes plus or minus spikes or limited variability. Then we do the same as what we did in the last experiment in voltage clamp. We were doing it with the current clamp. We're topically applying gabazine. So we block GABA receptors. The cell becomes much more electrically compact, much more excitable, and then for exactly the same sensory stimulus, you now get on average between 5 and 6 output spikes. And if you look what happens in the presence of gabazine, that here you need summation. In control, you need summation of EPSPs to get this burst of output spikes. So in terms of the number of input EPSCs compared with the number of spikes is always lower. But when you block inhibition and the cell becomes much more electrically compact, then what you almost see is a one-to-one relationship. So the granule cell almost becomes a relay. So for every EPSP that the cell actually receives, it generates a spike. So it almost removes the fact that it's processing any information. It's just relaying what the mossy fiber was actually telling it. And that's just equated there in the transformation ratio on the right-hand side. So inhibition and tonic inhibition is pretty important for setting the excitability level of the granule cell. And we'll go into the reason why that might be important, because I guess the first thing you think here is going, well, hold on a second, why you're actually suppressing spikes, so how can that be useful? Because wouldn't it be better if you actually got more spikes out for every stimulus you give? But hopefully by the end of the talk we'll sort of identify why having a level of tonic inhibition there is actually useful. So one, when you're using pharmacology, it's a when you're using pharmacology in vivo, it's a relatively blunt tool, and you've got to be careful because when I said I'm just topically applying gabazine or a GABA receptor antagonist to the top of the apical or the surface of the brain, but you have to remember that if you think of the anatomy or the gross anatomy of the cerebral cortex, that drug is coming through the molecular layer, past the Purkinje cells, past the molecular layer into neurons, then down into the granule cell layer. So it's basically blocking all GABA receptors on the way through. It's not selective in any way, shape, or form. But the beauty is that we're looking at the input layer. So actually, we don't really care what happens above the granule cell. We're only interested in what happens if you actually block inhibition in the granule cell layer. So it doesn't really matter what's happening upstream in these experiments. But one important part is that you're blocking any GABA receptor. So what if mossy fiber terminals, which are releasing onto granule cells, actually express presynaptic GABA receptors? Then the effect that we see here could just be as a result of changing the probability of release or the excitability of the mossy fiber. Then,
But it means you just show in your previous slide that the number of EPCs is the same in both conditions? And you
yes,
get
but
it
you
from
have to look at the amplitude of these EPSPs, because if they come in double the size, then if you need a summation of smaller EPSPs, but the first one comes in because it's 3 times the size it was before, you don't need that level of summation. So then, because it's changed the probability rates or the quantal content of presynaptic, it's always an argument people come back, how do you know that you haven't actually changed the input as opposed to changing the excitability of the cell or the target cell that you're interested in? But to check that, it's because it's such an electrically compact cell, we can switch into voltage clamp. We have really good voltage clamp for these cells. And then we can look at, in voltage clamp, the MOSI fiber. So we're just using the granule cell as a receiver to what the MOSI fiber is telling us. So here's EPSC. So when you give the sensory stimulus, you get this burst of MOSI fiber input, which is on the order of about 5 or 6 EPSCs. Then we can apply gabazine and then look at the sort of release characteristics of the MOSI fibers. And we find that it doesn't affect the number of EPSCs, doesn't affect the sort of the spacing between the events that are being released. The latency to onset doesn't change, or the actual burst duration. So to all intents and purposes, blocking GABA receptors has not changed the MOSI fiber to granule cell transmission, but it does change the excitability of the granule cell, and you get much more spikes out. Okay. So what does this mean in terms of what I was saying before? Isn't it better that you actually get more spikes out than less spikes out in a granule cell where you give a sensory stimulus? So when we sort of step back a little bit and have a look at the bigger picture.
Sorry. The location of the receptors in the dendrite.
Yeah.
So how exactly do you change the excitability of the cell? If you record roughly the same EPC in granular cell, and most of your inhibition is effective.
Well, most of the synaptic inhibition comes on to the dendrites. In terms of the tonic, it's extrasynaptic receptors, so they are both on the dendrite, they're along the dendrites, and there is some evidence that it's on the soma as well. Because this is ambient GABA that's activating it, so it doesn't have to be at the synaptic release site. They're not at the synaptic release site, so they're everywhere but the synaptic release site. So in terms of tonic inhibition.
So it's tonic inhibition all over the cell.
So yeah, because it's extracellular GABA that's activating it, so it can be pretty much anywhere. So that's how it changes the overall excitability across the entire cell. But then whereas the phasic is coming on specifically to the dendrites, then whatever it's changing is initially at the dendrites, which then propagates. But it's only 10 microns, 5 microns. So in reality, it's isopotential across the entire granule cell, even with its dendrites. So whatever you're seeing there is actually affecting the whole cell anyway. So if we sort of scale back a little bit and have a look at the same sort of experiments in current clamp, we're giving the same sensory stimulus, but we can also look at the spontaneous activity within granule cells. So spontaneous activity people sort of classify as noise. Obviously it's an intact system, so it's not noise, it's the network being active, but this is, let's say it's activity that's not associated with a sensory stimulus. So we have a look in control here. We give our sensory stimulus, and you get a nice burst of, or time lock burst of, on average, about 2 to 3 sensory volt spikes. And the background spontaneous firing rate is on the order of about 0.2 to 0.5 hertz, so quite low. Then when we apply gabazine, block all GABA receptors, much more electrically compact cell. And then if we look again, still with the sensory stimulus, we get nice time lock spikes, but now on average instead of 3 spikes, you're getting 5. But if you have a look at the spontaneous, or spikes are not associated with sensory stimulus, there's a huge increase in the amount of spontaneous firing. So if you sort of think about what that might mean in terms of the cell discriminating what's a salient sensory input versus not, if I was to say, okay, randomize this raster and then tell me where the sensory stimulus is given, because there's only single spikes and you get a nice burst of time lock spikes, if it was across here, you would say, yeah, there's a sensory response there, that would be fine, and you probably wouldn't make many mistakes. But if you go over here and randomize this raster and say, okay, where was the sensory stimulus given? probably say, you could say that there was one there, one here, across there, one down here, one down there. So the amount of sort of false positives would be massively increased. So it appears that to a certain extent the ability of the granule cell to be able to discriminate what the salient sensory inputs or sensory features it was getting is diminished when you remove this tonic inhibition. And to cut, well, I mean, you can see that also from the peristimulus time histograms when we control here, see nice time of burst of spikes. And yes, you do get an increase in the sensory evoked spiking, which is about, let's say, twofold, so from 3 spikes to 6 spikes. But in terms of the spontaneous spiking, there's a 6, 7, 8-fold increase in the level of spontaneous spiking. So in terms of when you look at the signal to noise, which is the important part in terms of sensory information processing, the signal to noise ratio is actually decreased. There's one thing I've missed out a little bit of work we did on this just to sort of reduce the complexity. But what is an inherent problem with using pharmacology in vivo as well? Gabazine, I said, is a GABA receptor antagonist. So it blocks all GABA receptors. And the problem is these extrasynaptic receptors have a specific subunit composition, and the synaptic ones have another specific subunit composition. But these drugs cannot differentiate between the two. And unfortunately, there isn't selective drugs, because what I'd love to have here as a pharmacologist to say, okay, I want to only target and block extrasynaptic receptors. But unfortunately, there's no pharmacology or no pharmacological tools to allow us to actually do that. So we put on broad spectrum GABA receptor antagonists, and what we did, because in terms of signal to noise ratio, what we're also doing is blocking the fast phasic input. So we're blocking all modes of inhibition. So how do we actually know that blocking tonic inhibition actually changes the signal to noise? So what we did, and I'm not going to go into details here, is we actually went back to in vitro slice preparations and used conductance clamp. You all heard of conductance clamp? In turn, to be able to inject currents, basically, to mimic what the cell would be seeing in vivo. So we can take all the recording parameters that we saw in vivo, the number of EPSCs that the granule cells see, the timing of those EPSCs. We can replay them back into our in vitro slice preparation and mimic what's happening in vivo. And then what we can do is we can do that with inhibition as well and remove the different components of inhibition to see how important each mode of inhibition was for controlling the number of sensory evoked spikes that were produced. So we did that, and what we found is that tonic inhibition alone basically modulates one spike out of that sensory response. So when we block all inhibition with gabazine, and we get from 3 to 6 spikes, so we now get 6 spikes, tonic inhibition is controlling one of those spikes. So we can remove from our in vivo data the effect of the other types of inhibition just to look at the effect of tonic inhibition. And when we do that, then we can pretty close to identify what the effect of blocking tonic inhibition does on the signal to noise ratio, and it appears to reduce that. So it reduces the ability of the granule cell to be able to discriminate salient sensory features. Is that clear? So that's blocking tonic inhibition, and that's sort of going to one extreme side, so you're just removing inhibition, or tonic inhibition. But what happens if you look at the opposite way? What happens if we actually enhance tonic inhibition? What does that do? If removing tonic inhibition decreases signal to noise, does enhancing tonic inhibition actually enhance signal to noise? It's a sort of simple assumption. And from a pharmacological point of view, it's a rather neat drug that's out there, where I said in terms of blocking selectively extrasynaptic tonic-mediating GABA receptors, there are no drugs that are good for doing that. But for enhancing specifically extrasynaptic GABA receptors, there is a drug called PHIP, which is very good at targeting only those receptors. So we can use this drug, again, topically applying it to the brain surface. This is looking in voltage clamp, again at 0 millivolts, so we're just looking at inhibition. These are fast phasic iPSCs. And when we topically apply PHIP, which enhances tonic inhibition, it'll decrease the excitability of the cell. We see that there is a sort of an increase in the standing holding current, which is indicative that you've actually enhanced this tonic inhibiting conductance. Remember before when we put on gabazine, you got a decrease in the holding current, whereas when you enhance tonic inhibition, you actually see an increase. And the beauty of this drug is when you apply it and it's enhancing selectively tonic inhibition, it doesn't have any effect on the phasic iPSCs. So it's not affecting the synaptic receptors, it's only affecting these extrasynaptic receptors. So it's a really quite a neat tool. And when we apply it, so again in control, here's your sensory stimulus, ear puff to the whiskers, get summation, and then you get a nice burst of spikes, on average about 3. Then we apply FIT, enhances tonic inhibition, makes the cell much less electrically compact, much less excitable, and then when you give the same sensory stimulus, now on average you get just a single spike. So it's not a burst of spikes anymore. And if we look back again in terms of what we did looking at both the signal and, let's say, the noise or the spontaneous background activity, again in control, we get our nice, get a nice time-locked sensory stimulus, on average about 3 spikes, and again in these recordings you can see that you get a low 0.2 to 0.5 hertz background spontaneous firing rate. You apply the drug, reduces excitability of the granule cell, enhancing tonic inhibition. Now you either get just a single spike for your sensory stimulus, or what we actually saw as well, that when you give your sensory stimulus, you actually got no sensory evoked response at all. So again, if we do the same thing as we did with gabazine, if it was asked to randomize these rasters, again, you'd probably be able to predict where the sensory stimulus was given pretty well. But if you was to randomize this raster, because it's only a single spike and there are spontaneous spikes, your ability to pick out where the sensory stimulus is given is significantly reduced again. Again, if we look at the sort of numbers, where under control conditions, you go on average about 5 or 6 EPSCs, which results in about 3 spikes. You get the same when you enhance tonic inhibition, but you get a significant reduction in the overall number of spikes. The number of evoked spike failures goes up to about 25%. So for 25% of the time you give the stimulus, you get no response whatsoever in a granule cell. Whereas before, when you find the center of that receptive field in control, every time you give that stimulus, you'll get a burst of 3 spikes. And again, doing the same sort of analysis as we did before, which is sort of indicated by the ground clamp recordings that we showed in the previous, similar to what we saw in gabazine, actually, when you enhance tonic inhibition, it actually reduces the signal-to-noise ratio, or the ability of the granule cell to be able to detect what, or at least be able to process the salient sensory information that's coming in, as opposed to the spontaneous background activity.
Is it a binary thing, or does it depend on concentration of?
Yeah. So yeah, okay. So you've just highlighted the other major caveat of using pharmacology in vivo. So that's exactly the question that we really wanted to know. Put it at that concentration, then put it this, and instead of necessarily having extreme here, control, and extreme there, we can see a nice curve, or whether it was a steep curve. It's nigh on impossible. So in terms of applying the drug, we put on a 5-fold higher concentration just to make sure that we get the right concentration for blocking down the granule cell there. But titrating that, you could maybe go in and put a second electrode in to puff locally specific concentrations. You can do it with light patch, you need to do that with 2-photon imaging targeted patching, which you can do in granule cell there at the moment.
So just making the tonic inhibitory kind of receptors always active?
Yeah, FIT's got in terms of the membrane biophysics, it's got kind of a complex way of acting, but yes, effectively it means that they're open. The open probability is enhanced, and they basically just flicker open and close a lot quicker. So the mean level of tonic inhibition goes up.
One thing I wanted to see and understand. So you claim that, for example, if you take and randomize the raster plot, you won't be able to say where is the sensory information. But the number of granule cells which converge onto Purkinje cells.
That's a different question. That's not the question I'm asking.
Yeah, but what you claim is that you're lowering the signal-to-noise ratio in just a percentage, but at the end of the day, the cell which actually has to decide what of the information containing the activity of the granule cell
three spikes carries the same information as one spike?
No, what they say.
The timing information, maybe.
What I'm saying, the timing information.
So that's an interesting feature, but I would not say that's a global point because that's saying that the cerebellum works entirely just on timing. So hopefully by the end of the second talk, I might convince you that that might not be the case. But the interesting point, so getting back to is, if the cerebellum is only interested in timing, let's say all the cerebellum wants to know is when is the onset of each of the sensory stimuli. One interesting feature which feeds into what you're saying is when you put FIP on, and we haven't gone in, really scrutinized it, but from a first pass look at the data, the actual onset of the first spike remains pretty similar.
That's what it seems in the last.
Yeah. So that onset will be, but but that would mean that it's negating any other information that's concerned. And what I showed before was that both the EPSCs and the spike burst duration is pretty reproducible. So I'm almost sure there's information in terms of how long was that stimulus, when's the on and off. So yes, there's definitely important information on the first spike, but I don't think that's all the information. So then the question that you'd be getting at is, what would be the outcome of just giving it timing? Just giving it timing of the onset of a stimulus.
And that would be the.
Well, that's a whole different question and beyond what we were trying to actually. I mean, it's a great question, but it's beyond what we were just looking at the input there to say, okay, how is sensory information processing actually regulated control as to what that means for downstream cells. Purkinje cells don't know. Interneurons will go on to talk about just in 2 minutes.
So one more thing. The argument you were just discussing only works if each Purkinje cell receives granular input from many granular cells that have the same receptive field, right? So if they play something, is that even the case? Do you know that? Do you know how many different receptive fields converge onto one Purkinje cell?
So from the cat, Hendrik Jean Tel's work where they did mapping receptive fields onto. In general, I don't think it's very well mapped in terms of, well, what we talked about before, remember, we don't even know what parallel fibers impinge on a Purkinje cell. Remember we talked about before, you've got these 2 millimeters, one, it's coursing through the dendrite, and it's got one synapse, and there's 200,000 inputs. We have no idea actually how that's organized. So in terms of really getting to the question of how does that cluster of granule cells propagate, is it distributed across many Purkinje cells, or is actually that one cluster of granule cells from one mossy fiber actually it will affect the Purkinje cell directly above it with the ascending axon, but as to the parallel fibers, to a certain extent that's not known.
Again, coming back to the onset of the stimulus, if you look at your last approach, the activity of the spiking is not during the entire duration of the sensory stimulus. So you have it in part of the sensory stimulus. So anyway, you don't have coding of the duration of the stimulus in what you showed in the last approach here. So
you mean that
what you're claiming is if I leave on.
Well, nothing occurs on the onset of any stimulus.
No.
So the where it's appearing is there's always an onset latency, and then the variability beyond that is pretty tight. There's not a high degree of variability because there's only like 40, 45 milliseconds that it's producing the 3 or 4 spikes.
Yeah, but how do you get this duration of stimulus in there?
By looking at the onset of the first EPSP to basically the last spike, which is the duration of the sensory response.
There's some like close over.
Yeah, I've got that in the second talk. Yeah. So it's also again where we're using the word cerebellum. This is CRUS2. This is dealing with fast, high frequency somatosensory input. So that's another important feature as well. I mean, I think it's in the second talk I'll actually show you when we're using 60 milliseconds, but we also use 200, 500 milliseconds, and the profile of how the granule cell responds to that stimuli sort of indicate the fact that these granule cells are really interested in sharp, fast sensory information coming in, and prolonged durations. They give some form of information, but it's not the same as the sort of first 100 milliseconds. That seems to be the important information that's coming in for these particular granule cells, but it will be very different if you go somewhere else. It's processing stimular input or processing somewhere else, which is a very slow time modulated input, where somatosensory seems to be much more about fast, high frequency bursts. so again we do the same voltage clamp just to say the same thing. What if there are these extrasynaptic receptors specifically on presynaptic terminals? We do the same experiment with applying FIT, look at voltage clamp at the sensory evoked EPSCs that come in. Again, we see no real change. It's again confirmation that it appears that the presynaptic terminal isn't expressing GABA receptors. So this is kind of what we're at the moment in terms of what the tonic inhibition may actually be doing in terms of, if we look at the signal to noise ratio, again, just look across here. In control, if we take that as the normalized standard, and then if we look in gabazine, we seem to get a decrease in the signal to noise ratio, and in the presence of PIT, when you enhance tonic inhibition, you also see a decrease. So it would sort of suggest that under normal basal conditions, the level of tonic inhibition is set to sort of enhance the signal to noise ratio in granule cells. Why might this be important, or why is tonic inhibition important? I think this is a sort of good indication of what, in general, neurons or cells might actually do. So for a granule cell, tonic inhibition appears to be pretty important, but some beautiful work done by Steve Brickley and Mark Farrand at UCL. What they did was they selectively knocked out these extrasynaptic GABA receptors, so basically wiped out tonic inhibition in granule cells, and had a look at the electrical excitability and slice of these granule cells, and also the behavior or behavioral phenotype of this animal. And you're thinking, okay, if tonic inhibition is important for excitability in the granule cell layer, and that's the input layer to the cerebellum, you screw that up, and you're likely to get some pretty profound motor deficits. To cut a long story short, a lot of data, electrical excitability in the granule cells was pretty much the same as in control. Which would sort of highlight the fact that, okay, hold on, maybe tonic inhibition isn't that important. Behavioral phenotype, exactly the same as wild type. No effect whatsoever. But the important part that they found in this Nature paper was that the granule cell massively upregulates a 2,4 potassium channel, which basically does pretty much the same as tonic inhibition. So what the granule cell was saying, like, I don't really care how you generate this tonic inhibition or this effective leak, but we're going to maintain it to make sure that our electrical excitability is maintained within a range that is, let's say, useful in terms of motor control. So I think it's a nice paper that highlights that whatever you're looking at, it could be superseded. So, and a note to that would be, if you do use knockdown experiments, knock out animals, so on and so forth, be really careful on the controls that you do, because probably Mother Nature has put in another safety system in there to upregulate something else that will take the place of whatever it is you're looking at. So getting back quickly, just the last couple of slides for this, and then we'll take a break. And getting back to your question again, what does it actually mean? Is this actually propagated downstream? For technical reasons, recording from Purkinje cells in the age of animals that we were recording from to actually look at the input to the cells, so we need to do voltage clamp, but unfortunately in Purkinje cells at that age it's just inherently incredibly difficult to get any kind of space clamp. So we took the other option of recording from the next, or a next downstream cell, so the local molecular layer interneurons which feed onto the Purkinje cells, make patch clamp recordings from those, and then do the same manipulations that we did down here to perturb or manipulate the level of tonic inhibition and see what effect this has on the parallel fiber input to these cells. So we see this change in signal to noise ratio that occurs in the granule cells, but is this propagated to the next downstream cell? So we do that, so this is recording from molecular layer interneurons. We're in voltage clamp, so each of these little circles are EPSCs, excitatory postsynaptic currents, which is a release event from the parallel fiber. We get a nice level of background spontaneous parallel fiber input to these interneurons, then we give our sensory stimulus, we get a nice burst of EPSCs in the interneurons. Then we topically apply GABA, or gabazine, comes down into the granule cell layer, will block GABA receptors present on the granule cells, make them much more electrically compact. We saw that increase both the sensory evoked response and the spontaneous, or the level of spontaneous activity, and that's exactly what you see here in terms of the PSDH. The background level of activity is massively increased, but the sensory evoked response is only doubled. So what we see again, similar to what we saw in granule cells, is you get a moderate decrease in the signal to noise ratio in the interneurons. So it seems whatever effect is happening in the granule cells is actually being propagated down to the see the other experiment by applying FITs. There's a selective enhancement of tonic inhibition in granule cells, reduces electrical excitability, and what we see is that from control in black here, you get a massive reduction in the sensory evoked response because you're either getting a failure or just one spike in the granule cell that's propagating to the interneuron. And again, when we look at the signal to noise ratio, has a significant 30-40% reduction. So it seems as though this effect is actually propagating through. So if you maintain the signal to noise ratio in the granule cells, this will also maintain the signal to noise ratio in the downstream interneurons. So sort of in conclusion from the first part in our sort of our main hypothesis or take-home message is that tonic inhibition, whereas right at the start I said, hold on a second, but in terms of the sensory evoked response, you block tonic inhibition, you get more spikes out. Isn't that useful? But if you look at the bigger picture of the signal to the noise, then in actual fact having a certain level of tonic inhibition is actually useful in terms of propagating the salient information from granule cells to downstream partners. We've looked at molecular interneurons, but as was talked about, the next important feature to look at would be what it actually means for the processing of information coming from many different granule cells down onto the cells. So we'll take a break there. how is information lost or gained at the granule cell layer? That's it.
I completely agree with you.
That's it.
Don't get me wrong.
The next study would be, okay, if you, because I mean, this is no point. So the conclusions of the paper are entirely valid because what is seen in the granule cell layer can be propagated to the interneuron, so that was going to change the interneuron. So this is another point. If you're changing the frequency and the pattern of input or output that the interneuron is actually producing, that's profoundly going to change the input. So then it's a difference between what's the granule cell layer directly to the Purkinje cell versus the imaging. And they're not
Yeah,
meaning.
but for me, more important actually was the pause that actually was reserved in both cases. When you look to the in the raster plot of the flip and one before, you had a pause after the peak of the raster plot. It wasn't so.
A pause after.
Yeah, like you had like the raster plot looked like that, and then you had the pause, and then the activity came back.
Yeah, that's
and
one cell. It's not highly
okay.
reproducible across. So that's
Okay.
just
Okay.
In terms of
Because
causing the system, or no.
for me the pause is actually more important than Turkish answer.
Yeah, it's not like a Golgi cell where you see this shut off for 300 milliseconds where there's a massive reduction. Yeah, we don't see. I mean, it's probably embedded within there in clusters of granule cells, but that's not what we're sampling by going in with a single cell and sampling across.
Well, what would you answer to the question that I'm not so sure, but I think that the granular cells, not granular cells, Purkinje cells are just like preferable granular cells, like the one with the ascending axon. I don't know if interneurons also have this property that they have a group of granular cells which are more active on them than other granular cells.
Well, it's actually it's predicted there's only a small number of parallel fibers that are actually driving interneurons anyway. The sample is not that many, so I would say if it's going to really.
So if it's not that many, then it supports my theory that looking at the interneurons and saying whether you made
that's the equivalent argument of saying never record from a single cell because it doesn't give you the whole information. That's not exactly.
No. What you said, I went to interneurons because Purkinje cells are damn hard to propagate. So I went to a cell which I claimed to be as good as looking at Purkinje cells.
When did I say that?
I had it in my head.
When did I say that? When exactly did I state that looking at an interneuron is exactly the same as looking at Purkinje cells?
No, but it is true that it's sampling the same population of parallel fibers.
This is a way of looking at parallel fiber activity, which is the propagation of the signal to noise ratio differences that we've seen. That's all I'm saying. Otherwise, I would have done current clamp because actually, recording from interneurons, you want to see what's the effect of that signal to noise. It's not my question. The question was, is it propagated to downstream cells? And the simple conclusion would be yes, it is. So a Purkinje cell is highly likely to see the same SNR changes. As to whether that makes a difference, I don't know. Definitely don't know.
Okay.
But it definitely changes.
I agree.
Which would be in itself either result would be interesting because if the Purkinje cell doesn't care, that's equally as interesting.
No,
because no matter what the heck you do to the granule cell there.
No, it definitely doesn't care. It means that it will have intrinsic mechanisms that will allow the growth in a certain range of semiconductor.
Yeah, but the endpoint result of it doesn't matter. Because whatever mechanisms you put in there, the end result of the Purkinje cell spike output, if what you're saying is, it doesn't matter what mechanism. I'm using tonic inhibition, the 2-pore potassium channels will do the same thing.
It's a long discussion.
Well, it's a different discussion. It's your take on the fact that it will or it won't, and we don't know.
No. The thing I'm saying is that it probably won't matter, let's say, for handling a specific sample information, but maybe over a long time scale, it might affect, I don't know, the ability of cells of the system to learn.
So one thing I would say with the FIP, if you look at that, in terms of M-glular activation, so if you say that look at a single, this is where it is useful, if you look at a single granule cell, which meant, or a small cluster of granule cells, and they all are to a certain extent can impinge on the same area of a dendrite.
Okay.
And if you're firing 3 spikes or 4 spikes at 100 hertz, you get M-glular activation.
Yeah. Okay.
If you get
one
spike coming in 4 times at the onset of the stimulus, you don't.
So it will affect the plasticity.
It could affect a whole manner of different things. That's why I'm saying that 3 spikes has to contain more information that's where I think probably the
Thank you.
interesting features will occur. But you would need to know the whole map of where all the inputs are coming from to the Purkinje cell to be able to stimulate those granule cells in a way that's faithfully reproduces what our sensory stimulus, and that we're way far off from being able to do that at the moment. Then if you do conductance standpoint, any particle interpolation, which are sort of you're going to recruit fibers which have maybe got nothing to do with this, and that's where my problem arises, and kind of one of the reasons I didn't go to Purkinje cell was just too hard for me to decode what the hell is actually happening. Whereas at least in the neurons, you just strip it down, you go, okay, in general, do parallel fibers change their value? You can make the loose assumption that across the board, in the interested granule cells, it's bound to, or more likely to have an effect.
I have another question. Tonic inhibition, how fast it could go on and off?
Again, another good question. It's because tonic inhibition is a real slow modulation.
Yeah, I know. So, you
So
how quickly could you imagine that the extra anti-GABA could be cleared off? If
well, so there's another more complex aspect. If you think of it in vivo, neurosteroid modulation, mood, level, anxiety, menstrual cycle can have profound effects on tonic inhibition. So instead of using the drugs, you can use neurosteroids to massively enhance, well, that's what happens, massively enhances the level of tonic inhibition in females during the estrous cycle.
in the cerebellum?
Yeah.
Okay.
Yeah. Ishvan Modi's done quite a bit of
Okay.
work on the effect of two. I can't remember which.
Where is the GABA coming from there? In that case.
Oh, well, so the ambient level of GABA, it doesn't matter, it'll be the
Okay,
same
so
level of
he
GABA,
does-
and then it'll potentiate the
Okay.
effect of that GABA.
Okay, so but he doesn't know the mechanism.
So it's still, as I said,
Okay,
still
yeah.
debating where the
Yeah,
heck
okay.
this comes from, because there was George Augustine had a paper out in Science about bestrophin channels.
Okay.
I hadn't heard of them before, but they reversed.
Yeah.
They basically reversed and they pumped chloride out. So,
Yeah.
and when he knocked out this bestrophin channel, he
Yeah.
didn't see tonic inhibition. But Steve Brickley, who did the work I talked about there, says that basically bestrophin channel is initiated when you cut that slices. Again, that's a debate that's going back and forth.
This is the type of facts I really hate to hear. Like, oh, so what you're doing is actually another level of complexity.
But it's the problem with doing.
Anyway, so if you know how fast it could be turned off or on or whatever, like what's the time scale that is for being
I
operating?
would imagine that this is running in minutes to.
Minutes.
Yeah.
Okay, so then it wouldn't be relevant for anything that's going on, any ongoing behavior.
Really?
I mean, in the sense of
So
it doesn't change.
your mood doesn't change your everyday
Yeah,
life?
no, but I mean that it doesn't. It could not affect anything that would be happening from moving from here to here.
It won't change. It won't change the fast decoding of the system.
Yeah.
Basically.
So it can change the state of the system, how it is encoding.
Exactly.
But
That's
it
exactly
would,
what I think tonic inhibition. It's like a slow modulator.
So this what I was thinking. I used the CGM part when I was thinking of it. You could like promote saying it is certain
לא, אבל
I
יש
mean,
כאן איזה
so
משהו
this
שאנחנו
would be too
אנחנו
slow.
רוצים לראות את הסך סוליד
It would not be
אוסילטורים,
relevant
אנחנו
for what's
מצביעים
going
על
on
זה.
at this moment.
יש לנו איזושהי בעיה, זה
So I,
בטוח.
what we're going to talk about next is
אבל
the
מה
phase
שאני
of
חושב
spillover,
שכן באמת
Yeah.
מעניין,
point to
שאם
point,
זה באמת
Yeah.
minute to millisecond to millisecond type organization of what's going on in terms of regulating but I think, I definitely think this is a slow background setter. And again, when the other caveat to this as well, which what I class as controlled, what the hell's controlled? What the hell is controlled? Because I have
צריך לדעת כמה מזה
with ketamine
כמה מזה
silencers, so that's
לקחת
going to
וכמה
be
מזה
slightly different. I mean,
לקחת. זה לא כתוב
I'm perfectly happy to
יש
show
הבדל.
all the weaknesses. And
זה
what
לא,
happened to
אפילו,
that
אבל
back?
זה
What
כן
happened
כזה
to the
לבד,
matches
זה
prior
כן
to
שבלי
actually
שום
being
דבר מסביבו.
phased?
But actually, I think that this is the
זה לא
human
כתוב לו
version
בגנום, אתה צריך
of
20,000 מזה
any
ו-15,000
active
מזה.
cycle in vivo. The fact
יש
that
שם איזשהו
actually do
מנגנון
a
רגולציה,
roughly
אם הוא לא
stable
יורד,
Because you put that weight in
Yeah.
the way I could do any of
אם
these
הוא יורד יותר מדי, אז
experiments.
מוסיף פוטסיום,
But
ובסוף הוא מגיע
I guess
לאיזשהו
with
שיקום
the not
משנה.
knowing where the
באמת ההתפתחות של התאים האלה,
what we don't know is whether it's like this
אבל כל אחד פותר את זה בצורות קצת.
or like that.
והם כולם פותרים.
Which is a question of can you titrate it? Because I don't think it's like that. There's no way that there would be one because I can't find an optimal point using the rough technique. More than likely it's going to be something like so there's a window where you can see because I'm design everything's okay, but then if you really go extreme,
conductance of the
find me the way to prove it, and then you sometimes find a way of testing it.
Then the way to test it actually will go by the Milka suggestion. If you know that, for example, in the menstrual cycle you have changes in the tonic inhibition, what you can actually do is you can actually try to measure in animals during the menstrual cycle, different points of the menstrual cycle. What is, what like the fitness
A natural.
exactly, and then you will have both the model and the
This one nobody's done that a little bit, I'm just looking at the
if you have the construction of garlands, you can replicate really good, quite easily.
That would be a nice way to do it. This was just a sort of first pass to say, okay, on the extreme side.
Yeah, exactly.
The next interesting part about it physiologically, where does it sit and where does it sit on here normally?
Really? So we have
And that's something we're going to do.
Yeah, obviously it's going to be difficult. It's actually a good way of saying, oh, let someone else do that.
It's just tricky enough because the problem is just taking, you saw what happened with the knockout or the perturbation of that, how quickly it would actually change it to off-regulate something else.
And also, another point is that the data center information that you're reading here is actually the data center information that is start and what happens if you go for the particular it's basically a continuous so I'm not sure that it's actually the same effect in the vestibular system as you see here.
That's entirely true, that's where we're not buzzing. And she's talking about baseline, but in terms of sensation, I mean, we don't, in terms of under anesthesia from primary recent work, we don't even know what it's like outside when the animal is actually getting that sort of.
It's actually quite funny because we got papers from Physiology to review, and he had this like entire model of expectation coming into the holograph cells and effects and stuff like that. And then it states what's supposed to be the frequency of it, the unipolar wash by the multiplier. And when you go to the literature, it's anywhere from 5 cells to 40 cells. Why not? Just pick whatever you want. When I say all this multiplied went to my mind. How did they do that?
Pure chance of random.
But how they came in Prince of Contain that sort of
We got however many time from our wing recordings. We bumped into them every other day. Really? We just sheltered them. We don't really need to, it's a sort of, we've got an ongoing project. It's even less random when you go back and find some real thing. Yeah.
For me it's just like
it is. White patches. A little bit of experience and ingenuity. White patches and I don't think there's any skill involved.
if I explain someone what you're doing. So this take this watermelon and I small things. What do they feel itself?
Tip of the seat and close my eyes.
And the watermelon before you exercise it is really going to
Yeah, again, I've developed this project for sanity.
I talked to Chelsea yesterday. Do you have a practice of between two spots?
I would imagine so, yes.
So let's meet. Let's set it into the side.
Yes.
talk a really smart guy and guy
שם
that
הוא
works
מה?
with smart
Yeah.
איפה
Well, I gotta get some coffee.
I'll get some more water actually.
Thank you.
זו שאלה שאולי יכול להיות מעניין למישהו לבדוק ולעשות לנו מחקר אותי אישית, חוץ מזה או שזה כזה דבר סובייקטיבי
חלק קשה יותר כאשר נותן את הסולם הזה של המינימליסט. אני מתייחס בדיוק לדברים הלא רלוונטיים, זאת אומרת, אף אחד לא חושב שהאחווה כואב לו פחות שכואב לנו. בכל זאת אנחנו צריכים לשים לדברים ולא לדופים. הסיבה היא לא הכאב. אבל הסיבה היא, אני חושב, וזו הסיבה שבכלל מעניין אותנו המוח, אני מסכים איתו עם ההגדרה, מה שמעניין אותנו זה המים ולא המוח, זאת אומרת, לפחות זה גם ברמות מסוימות, אבל מה שמעניין אותנו זה האינטליגנציה של המוח, ולאו דווקא הכאב. עכשיו העניין הוא שככל שאינטליגנציה ויותר פרפרנס ושפה, ברגע שליכולות האלה יש גישה לסובג'קטיב אקספיריאנס, נהיים הרבה יותר מורכבים. ואז הכאב שלנו אחר באופן איכותי מהכאב של האחווה. והוא אחר במלא מובנים, אנחנו מסוגלים להכין לעצמנו כדי להכין מטרות מסוימות, מה שהאחווה לא יעשה. מה שבטח עוד יותר נמוכות לא יעשה.
להצמא את הרגליים ושנשתפכים הכל.
ברמה הזאת זה נורא תעשה. אבל בנקודה אין לו רצון גול כאלה שנזירים בדיוק יצומו וזה, יש להם. הם רוצים להם. זה לא הנקודה, אולי זה אתה הולך על מטרות אבסטרקטיות ואתה מתעלם לחלוטין מדברים אחרים, שבגלל יכול את כל הסובג'קטים ולהכניס אותם לתוך במידה מתעלם, זה הרגע, אבל זה האבן של כל העניין. זה לא משהו שהוא לא יודע, הוא בוחר ומודע להתעלם. מה?
הייתה לו תשובה גם לזה, למשל, שהאינטליגנציה היא לא משהו שמתחיל מנובע כמרות בהיסטוריה כמושג של
Okay, let's get started on the second half. So we're going to focus, we've done, or we've at least covered certain aspects of the importance of tonic inhibition on sort of shaping how important or salient sensory information coming through granule cells is. So now we're going to switch to the other side of the other two types of, or modes of inhibition, that is direct, sort of, or at least much more direct point-to-point communication from Golgi cells, the inhibitory interneurons, to the granule cells. So this is the phasic, or the fast activation of GABA receptors, which have a fast desensitization as well, which gives you a really short point-to-point communication. And this second sort of form as well, which is spillover. As I said, the glomerulus has this glial sheath, so it sort of traps a neurotransmitter within this glial sheath. So when you get high-frequency activation of presynaptic GABAergic fibers and it releases a lot of GABA into the extracellular space, then what you can get is spill out or spill over of GABA from that synaptic cleft, which will activate perisynaptic receptors, or you can get the situation that you can get activity of an interneuron axon terminal, which is not sort of directly contacting a granule cell here. It's contacting another granule cell over there. But if you get high frequency activation here, GABA spills out and activates receptors on a different granule cell. And this is what is sort of classed as spillover or spill out of transmitters. So we'll sort of focus down on what our sort of first probe into what these might actually mean for information processing in granule cells. And then the first lecture sort of showed that basically there's nobody in vivo has really dissected what forms of inhibition are actually present, and definitely not what they could potentially be doing and why a granule cell actually needs these sort of three different types of inhibition. So in terms of inhibitory input, fast phasic inhibitory input, if you go back to what it's useful for, I mean, this is sort of a general view of feed-forward inhibition, what it's good for, and this is work done by Massimo Scanziani, and this is in the hippocampus, I think. But in general terms, feed-forward inhibition, which arrives, it's usually disynaptic feed-forward inhibition. So you get monosynaptic excitation, which comes in first, then you get the same fiber which activates a nearby interneuron, which then feeds forward onto that same cell, but there's a delay of about 2 milliseconds due to synaptic transmission, and so the inhibition comes about 2 milliseconds after the excitation. And what this feed-forward inhibition does is sort of reduces the temporal window for synaptic integration, meaning that if you don't get a second excitatory input coming in within a short space of time, it doesn't actually summate because it's shunted by the inhibition coming in 2 milliseconds later. And what that means in real terms is, in control or under normal circumstances, when you have an intact feed-forward inhibitory circuit, it basically keeps the precision of the spike timing in a very tight window. Whereas if you knock out this feed-forward inhibition, basically you get summation at any point, or at least within a much larger window, so you can get summation and you get spikes at a highly variable time point after the initial stimulus. So what feed-forward inhibition does is really constrain or maintain the temporal fidelity or the precise timing of spikes. So these are recordings we made, again, this is in juvenile rats under anesthesia, but given the same sensory stimulus as we were talking about before, so it's just an air puff to the whiskers or upper lip, 60 milliseconds, and this is recordings from granule cells again at -70 in voltage clamps, so we're looking at transmission, excitatory transmission from the mossy fiber to the granule cell. And again, we see this sort of burst of about 5 or 6 EPSCs, and they're nicely time-locked to the sensory stimulus. When we switch to 0 millivolts, so we just raise up the membrane potential to 0 millivolts, which is the reversal potential again for excitation, so we're only looking at inhibition. So in the same cell, we can look at both the excitatory input and the inhibitory input it's getting during sensory stimulation. So you give that, and what we see in pretty much all cells is that you see a burst of fast phasic inhibitory input or fast phasic iPSCs, but also this long, pronounced, slow spillover mediated inhibition. And we see it in some cells, but this sort of activation, it's a sort of another body of work I'm not going to go into, but in some cells what we see is once you give this brief sensory stimulation, actually the activity of Golgi cells shuts down. And this has been documented before, so you actually get a decrease in the spontaneous iPSCs that occur in this cell. So, I mean, it was pretty much every cell that we recorded from that we saw, and we couldn't find cells that where you give your sensory stimulus, you would either only see the phasic iPSCs, or you would only see the slow spillover inhibition. It seemed to be that you would always get both coming together. And this input is not just from one Golgi cell. It's thought on average that there's about 6 to 7 Golgi cells impinging on one single granule cell. So this is probably the compound activity of about 5, 6, 7 Golgi cells being stimulated to produce the inhibitory input. So when we sort of split and what the profile of the different inhibition look like, this is it in the sort of the compound effect, and then we can split them out and subtract one from the other, so we get these nice burst phasic iPSCs, which are time locked to the stimulation, and then this sort of subtracted slow spillover, which can last up to 300-400 milliseconds, even through the sensory stimulus is only 60 milliseconds. So it's a long inhibition, well outlasting the length of the stimulus. And from in vitro slice studies where they're using stimulating electrodes, the studies that have been published show that there is a feed-forward inhibitory circuit. So this would have inhibition arriving about 2 milliseconds after excitation, which is the same as classical. It's in the cortex. There's many other different brain areas that you get this 2 millisecond time lag between excitation and inhibition. So we just want to look and see whether this feed-forward circuit that's been proposed in the cerebellum was actually present when we're providing sensory stimulation. So we give our sensory stimulus, and we're in the same granule cell recording from either 0 millivolts to look at inhibition, which is shown in blue, or at -70 to look at excitation, which is in black. And when we gave the sensory stimulus and looked in the same cell, what we tended to see in this particular cell here is that inhibition actually arrived before excitation, which generally can happen with a classical feed-forward inhibitory circuit. The inhibition always comes after because of the synaptic delay from being a disynaptic pathway, as opposed to the excitation, which is monosynaptic, so it occurs almost immediately. So this was interesting. We saw this in a couple of times, and my predecessor in Mike's lab, Mike Heuser's lab, Paul Chatterton, observed this in a couple of cells, and has been seen by a couple of other people as well. And what we found was, on average, I think there was about 7 out of 9 cells would always see that the inhibition arrived before the excitation, which is really rather unique in terms of the way that we were thinking about how the cerebellar circuit actually worked in terms of inhibition, which was always thought to be a classical feed-forward circuit. In terms of the sort of scaling of the conductances, the excitation is pretty similar to the inhibition, and it's sort of matched that in terms of the phasic and the spillover, whenever you get higher phasic, you always get higher spillover, which is probably just reflecting the fact that you're either recruiting more Golgi cells, and when you recruit more Golgi cells, you get more fast phasic, and you also get more spillover. When you recruit less Golgi cells, you get less phasic and you get less spillover. What we were talking about earlier in terms of what this is somatosensitive or ear pulse stimulation to the whiskers. What we were talking about before, whether the onset of the stimulus is important or what it looks like when you start to elongate these sensory stimuli. So we did that experiment, came back from a reviewer to say, okay, well, it's a very defined, arbitrary 60 millisecond ear pulse you're giving. Why? What happens if you give more elongated stimuli? What changes? So we did that by doing the same sort of experiments. This is in voltage clamps, so we're looking at mossy fiber transmission to granule cells, so these are EPSCs. And we elongate the stimulus to 200 milliseconds, and what we see is a sustained, or at least an increase in the number of EPSCs that you get, and you can increase that further to 500 milliseconds. But getting back to the discussion we were talking about before, if you actually look at the frequency profile of the input, if you go to 60 milliseconds, which I'm showing here, basically you get this curve that comes straight back down to baseline. If you elongate it to 200 milliseconds, you still get this really fast high frequency burst, but it comes down to start to plateau for the remainder of the sensory stimulus that's about 50 hertz. And if you go even longer, you still get this really fast high frequency input, but then it comes down and plateaus for the remainder of the stimulus. So it would appear in terms of the way the granule cells might be integrating this information, that potentially this is where, and we also looked at the spike output, and most of the spikes occur within this first sort of 100, 200 milliseconds. So it seems that at least these granule cells processing sensory information seem to respond better to short sort of high frequency or short duration sensory stimuli, which I guess if you think in terms of whisking, that's a sort of, if you're going to do active touch and whisking, it's going to be very short periods of time that's actually in contact with something. probably potentially the way the system's set up to just process that information, whereas the chance of a whisking mouse holding its whisker on an object for 500 milliseconds then coming back is kind of not the way the system works. So that's just our sort of pet way of thinking about it. So that's the excitation scales. So you get, about 5 or 6 with 60 milliseconds, goes up, so on and so forth. And the duration of the burst is elongated, although there is a frequency change during that burst. But if we look at inhibition, so we're now switching to 0 millivolts and just looking at the inhibitory input. We give 200 milliseconds again, and we give 500 milliseconds. What we find is that the number of centrally evoked IPSCs doesn't appear to change. So irrespective of the duration of the stimulus, you still get the same number of fast IPSCs. And if you look at the duration of the spillover, it doesn't seem to change either, which is pretty interesting considering the excitation from the mossy fibers is increasing sort of, let's say, linearly with the duration of the stimulus, and Golgi cells are receiving mossy fiber input. So obviously Golgi cells are receiving more and more input, but they choose to actually disregard that extension of the stimulus and only put out the same sort of response each time. That seems sort of counterintuitive, but if you actually look at the Golgi cell literature, Golgi cells are inherently bad at following high frequency stimuli. What they end up doing is just firing one spike at the onset of the stimulus, or maybe 2 spikes, and then it just falls away, and they don't really follow the high frequency input. So it's probably to do with, I guess, a bit to do with the timing, or to do with the fact that Golgi cell impact is maximal around the point where there's the most amount of information that's important to the granule cells coming in. Well, that's our take on it. So it's an interesting feature that even though you increase the stimulus duration or the amount of mossy fiber activity, Golgi cells just seem to put out the same reproduced response. But the spillover is lasting well in excess, or at least it can follow right up until the end. Even though it's a 60 millisecond stimulus, it's still giving a 300-400 millisecond spillover, which is there well after the stimulus finishes. So, I sort of alluded to that in the first bit, that this is the classical feed-forward inhibition is what the organization was thought to be, or the pathways that was thought to be present in the cerebellar cortex. But we were sort of proposing the idea that there might be parallel feed-forward inhibition. And what in terms of the work that's been done up until this point is being done in vitro in Angus Silver's lab, really quite nicely mapped out the importance of stimulating Golgi cell input and stimulating mossy fibers to show this classical disynaptic feed-forward inhibitory pathway, which was really nice, and it's fine, but it depends on where you're actually stimulating, because you can recruit feed-forward inhibition in vivo, but we don't think that it's actually the primary pathway that's being activated during sensory stimulation. So, in terms of classical feed-forward inhibition, this is what the sort of picture looked like, or what people would have thought before. The single mossy fiber comes in, so it gives monosynaptic excitation to the granule cell, so fast excitation, and then you get disynaptic feed-forward inhibition that would arrive maybe 2 milliseconds after the excitation. And as I pointed out before, this would be proposed to narrow the window for synaptic integration and maintain precise spike timing in granule cells. So that's the existing. So we looked at, it's been found in slides that presumably you can recruit feed-forward circuits in vivo. There's no reason why you shouldn't. So we went back to look at whether that was actually true. And what we can do in voltage clamp is sit at an intermediate potential. So minus 70 millivolts, you look at purely excitation. 0, you look at purely inhibition. But if you sit at minus 40 millivolts, you see both excitation and inhibition are going in opposite directions. So it's a nice little tool to be able to actually have a look at where inhibition excitation comes in terms of temporal order. And basically what we found was that in terms of the inhibitory input, you see fast basic IPSCs mainly at the onset of the stimulation, which is what we had seen previously. But if you look at the probability of actually seeing feed-forward events, so events that you see an excitation followed roughly about 2 milliseconds with an inhibition, I should say the other way, excitation followed by inhibition about 2 milliseconds apart. Across all cells, we only saw about a 20-25% probability that you would see anywhere in a burst feed-forward like events. So they're there, they're definitely present, but they don't seem to be the predominant form of inhibition that's coming in, or the pathway that's being activated. for feed-forward inhibition, it's always going to be precisely timed because it's the same MOSI fiber that's activating excitation that would be activating inhibition. So that 2 millisecond delay is going to be pretty faithful across many trials. But what we actually found was that across the bursts, iPSCs would become more and more highly unreliable. So that the jitter that was on the timing of those iPSCs as you go across the burst was really unreliable. So it doesn't fit with being a strictly timed feed-forward circuit. So it's there, but we don't think it's the main pathway. So what we started to propose, and going back to the fact that inhibition is arriving before excitation, if you go to the feed-forward circuit, it's impossible. So the same fiber, you can't get a disynaptic delay coming before the monosynaptic excitation is coming in. So what we began to propose was the fact, well, maybe there's actually parallel feed-forward inhibitory circuits. So there's still feed-forward, but not in the classical sense that it's the same MOSI fiber that's activating both the granule cell and the Golgi cell. And what we're proposing at the moment is that there's actually different parallel feed-forward circuits. The different MOSI fibers will activate Golgi cells, and they will be different from the MOSI fibers that will activate the granule cells. So in that respect, to get inhibition coming before excitation, you would have this MOSI fiber 2 being active. It would recruit inhibition that would arrive prior to the activation of MOSI fiber 1 input.
Is it not anatomically one MOSI fiber would go to granule cell and go
So it's a massive hole in our understanding of the cerebellum, similar to what we talked about yesterday. We don't know which parallel fibers go to a Purkinje cell. Even at the basic anatomical level, we have no idea the organization of the MOSI fibers and where and how that's organized with respect to granule cells and Golgi cells. Adam Hanman at Geneva Farm is really going after that just now. And he's doing all molecular genetic mapping techniques in vivo and then taking it out into the controlled situation of taking a slice preparation, and then he can really go, well, there's an orange MOSI fiber here, there's a green one here, there's a granule cell I'll record from, they both impinge on, and start to piece together the system. But that's about the only way that we're really going to start to understand. So we have no idea, which is why I say this is our sort of pet theory at the moment, but we've got no anatomical evidence to actually back up that this is the case. So yeah, this would be parallel MOSI fiber input that would actually account for the fact that you can get inhibition arriving prior. And if you look at the latency, which is important, it's not just a case of 1 or 2 milliseconds before. I mean, we can get cells where 10 milliseconds before the excitation arrives, you can get inhibition coming on. So it begs the question, okay, so why is it set up this way? We know why, like let's say in the cortex you get classical feed-forward inhibition to control precise spike timing. So what is Golgi cell inhibition actually good for? As I say, this is what you're seeing in the sort of the hippocampal or the cortical.
Go few slides. So basically, is the Golgi cell such a faithful follow? Is it kind of known that an input from a single MOSI fiber will trigger a spike for every MOSI fiber input?
No.
Because so your argument for the 2 millisecond delay, this would be kind of reasonable if you had like small type of inhibitory neurons that the single input would trigger them and very faithfully. But if it's in vivo and the Golgi cell is spiking and has some jitter, and then you have an additional MOSI fiber input, this could kind of, play different ways.
Well, one thing about Golgi cells, if the frequency doesn't go ridiculously high, they are pretty faithful followers of the first spike. But it still needs the compound input of, I think if I remember correctly, Angus Silver and Slice says that it's between 5 and 6 MOSI fibers, or Ingrid saying that, it's between, let's say, 5 and 10 inputs that are coordinated to actually give you that spike. It's pretty, if you get the receptive field for the stimulation, it's pretty faithful, but it just falls away afterwards. So you get the first spike, which is relatively precisely timed, but not that precisely timed. And if this is the compound activity of 5, 6, 7 different Golgi cells, you have to coordinate the activity of each of those precisely timed spikes. So yeah, the classical feed-forward system works in cortex, but it may not, it Okay, so what's classical feed-forward inhibition? We kind of have an idea of why that's important, exactly what Vicky's saying in terms of the close communication between interneuron and principal cell. And so what we did, obviously there's limitations in vivo, we can't control the stimulus, it's got a bit of variability in there, and what we want to do is basically look at, okay, if we change the timing of the inhibition, what effect does that actually have on granule cell spike output? So what we decided to do, because to give us a little bit more control, is go back into the slice preparation, record from granule cells, and change by putting in lead conductance, effectively using the conductance clamp that I talked about before. So you can basically, in the dynamic clamp situation, inject currents which will produce conductances of the size that are faithfully represent the synaptic input that those cells would be getting in vivo. So it gives you a way of sort of replaying in vivo-like trains of input into an in vitro situation. And it gives you complete control because obviously you can put any waveform you want in with whatever timing, whatever amplitude, so on and so forth. So this was in collaboration or worked alongside Tiago Branco, and we basically set up a number of different waveforms, both excitation and inhibition, which would represent the variability in the timing and the amplitude of the excitation that we see in vivo, and also the timing and the amplitude of the inhibition that we see in vivo. So, and we draw from a distribution to basically say that we're trying to cover the whole sort of, or at least map on the same type of input that you'd be seeing in an in vivo situation. And when we can do that, then we can control all the timings, and then what we did was we replicated, in the granule cell in vitro, replicated the sensory evoked situation that we would see under normal conditions. And then you can look at the jitter that you get on each of these are the first spike that occurs in the granule cell, and you can look at the sort of variability in spike timing that occurs. Then we can switch it around and go, okay, what if it was set up in a classical feed-forward scenario where we could just put the inhibition 2 milliseconds directly after the excitation? What would that actually mean for granule cell spike timing? And effectively what we find is that the granule cell, to a certain extent, doesn't really care where that inhibition comes in. It pretty much, in terms of the latency of the first spike, it doesn't really matter. But if you take out inhibition, then when I say no inhibition, the tonic inhibition is still present in both of these scenarios and in all of these scenarios. We're only blocking the phasic and the spillover. And when we take the phasic and the spillover, or the Golgi cell inhibition, actually, this is standard deviation of the spike latency, I see that actually spikes become more precisely timed when you take away inhibition. So it's the converse of what you say. If classical feed-forward inhibition in cortex and hippocampus precisely produces precisely timed spikes, the cerebellum seems to be the complete opposite. Golgi cell inhibition is actually increasing the variability in spike timing, which seems kind of odd. So that's in vitro situation. Can we see sort of indication of the same thing? There's obviously caveats to using a broad spectrum GABA receptor antagonist, but when we apply gabazine topically and we look at the timing of the first sensory evoked spike in granule cells, in control you can see there's a sort of jitter. When we block Golgi cell inhibition in granule cells, become much more precisely timed, much more time locked to the start of the stimulus. So the precision is actually enhanced when you take away the inhibition. You can see that down here, which in terms of the relative timing, in sort of relating an in vitro preparation, if you look in terms of the timing, 5 milliseconds versus 10 to 15, and this is using conductance clamp, we can pretty much faithfully reproduce what we can see in vivo, even though it's an in vitro situation. So it appears that blocking this inhibition actually reduces the temporal precision of spiking in granule cells. So you go, okay, well, what the hell is a Golgi cell doing? It's actually just interfering with the system. It doesn't seem like a logical, useful use of inhibition. So what is it actually doing? So what we then went back into dynamic clamp in the slice preparation in vitro to then have a look, okay, maybe it's not specifically about the timing of the inhibition that it's interested in. And when inhibition is going to be on 5 to 7 milliseconds before the excitation, it's almost going to be steady. That spillover current, which is 300 milliseconds, is going to be steady what is phasic and spillover inhibition actually doing? So what we did was we did the same experiments, but had a look at the interburst spike variance. So interburst spike variance is when we give repeated trials to the same granule cell, what is the variability in that spiking between each trial? And what we found is if you blocked inhibition or blocked the Golgi cell inhibition, it was pretty much similar to control situations. But if you looked across the entire population of granule cells and said, okay, let's take the mean sensory response, or the mean number of spikes that our stimulus produces in a granule cell, what's the number? And in control, as I said before, when you give this sensory stimulation, but this is in vivo, but in vitro, when you give this stimulation, you get a pretty faithful, reproducible sensory response of about, on average, between 3 and 4 spikes. But if you knock out Golgi cell inhibition, then actually now you get a huge spread of number of spikes, right down from 2 right up to almost 5 spikes. So actually the variability in the sensory response is massively enhanced. So actually what we're proposing, and we can bootstrap that, obviously this is a small number of cells that we've been recording from, but if you bootstrap that again, you can see in terms of the mean number of evoked spikes, there's a significant difference between the two. So we're proposing the fact that it's maybe not the millisecond precision, but more about the faithful reproducibility of giving the same sensory stimulus that the granule cell will faithfully give the same sensory response. Because if you've got a billion granule cells, you don't really want a high degree of variability, because then decoding that at the next level is going to be pretty insane. But if you can keep reproducibility across clusters of granule cells, then you might have the ability of decoding it the other side. So I'll leave you with that sort of question. There's a big debate in the field, and there's proponents of the fact that millisecond precision in the cerebellum is important for motor learning, motor timing, and motor control. We would throw out there, is it millisecond timing is important in terms of spike precision, or is it actually about the reproducibility of that sensory response? This is for the somatosensory input. I'm not saying that that necessarily scales across to other types of input in different areas of the cerebellum, but at least in the somatosensory area, or where it's processing the somatosensory input, I'm not so sure that millisecond precision is as important for reproducibility. So, just as a quick summary of the two granule cells, really simple cell, there's a billion of them. What are they actually processing, and why do they need these types of inhibition? Because I think in terms of computational significance, these different forms of inhibition bring something else to the play, bring something else to the table. In terms of tonic inhibition, maybe controls from a really slow modulated, because tonic inhibition, as we were talking about in the break, is slowly modulated. So maybe it's just a sort of a general setter of the excitability of granule cells, and in general the signal to noise ratio. And then the point-to-point communication between Golgi cells and granule cells is much more interested in actually controlling and sculpting the sensory response and the reproducibility of that sensory response.
It seems like a big effort, I think, what you're proposing. And basically, you're saying it's all about reproducibility. And in an environment where you're constantly stimulated and you want to keep that reproducibility, you're basically, what you're proposing is a constant level of spillover or whatever, which is basically a constant. You would want the
For that stimulus.
Yeah, but you keep getting stimulus. I mean, why
So the
have something that's the point of inhibition? I think is something that, or any signaling, something that's not intrinsic to the cell, is to have some modulation of it.
But then that's exactly it, because I showed the conductance levels, that if you get low, you don't just get one set level. You can get, if you get smaller, phasic, you get smaller spillover. But there was a whole range of, conductance, the average conductance was coming with phasic and spillover. So that it's not a case that Golgi cells will only put out a set level. That, depending on the stimulus and the amount of recruitment of mossy fibers, will change the amount of GABA that's released. That will then change let's say that maybe the frequency or the amplitude of that spillover, which then you get the dynamic control over. Because yes, if the Golgi cell just spits out exactly the same information each time, mossy fiber excitation, because if you put a set level of inhibition, but then it just becomes a tonic.
But what you're saying that's highly variable, from what I understand, is the input from the mossy fibers, and you want to transform that into a set output from the granule cell. Then I would understand this dynamic controlling.
Well, so the level of inhibition is going to be linked to most likely the level of excitation that's going to. They will scale together.
Okay.
But dynamically how they interact will be different depending on stimulus, depending on recruitment of mossy fibers. I don't think it's as simple as, but with this, giving exactly the same stimulus each time across all granule cells, then it's obviously completely different from the natural environment where it'll be a whole different change in different levels of recruitment of mossy fibers. So it'll be much more complex, but then this can scale depending on what level of mossy fiber activation you get. So you could shift that too. But the actual size of this will change depending on stimulus. Surely.
Coming back to what you said, the level of excitation and inhibition will scale together. If you have different mossy fibers coming to the granule cells and different mossy fibers coming to the Golgi cells, why would they scale together? You might have a group of mossy fibers that
It's entirely true. Yeah. But I'm saying that most likely do, because then you have a dynamic system. If they don't, then you're just having the same information coming in. So, but we also don't know where. Anatomically, we don't know how it's organized, and also the speed at which these are coming in. It might appear that the inhibition could be driven by trigeminal mossy fibers from a trigeminal system, whereas the slower excitation may come from corticopontine input.
and what you're saying basically is that the entire system that you have here is basically somehow to level up the play field. So if you get input from different sources, then this is just another way of putting it together somehow.
So potentially, yeah. And if it is trigeminal, it's fast and it's almost setting the. Not, I don't use the word threshold, but you know what I mean by it. It's almost setting the level of excitability.
Yeah.
5 milliseconds, 8 milliseconds prior to the excitation coming from. I mean, this is all hand wavy. We have no evidence to support this, but if it's coming from corticopontine with a delay, the slow spillover is already in place exactly when the excitation comes
But
along.
then you have a prediction basically. What the prediction that you will have is that if you go to different places in the cerebellum, which want to receive input from two distinguished different places, which have difference in time to the input, then this type of system would be less pronounced. This is the prediction that you're having.
Yeah, and that's why I said at the end that this is how it's working in terms of sensory information processing. But if you go to stimular or wherever else, so it's a slow time modulated input, this may not work in any way. But then the whole system's probably set up differently anyway in terms of being able to process that information. So,
but how would this fit with the worldview of this crystallized cerebellar structure? You roughly have the same anatomical connections between.
Same anatomical connections, but not the same information coming in. So, I mean, the point is you can have 10 inputs to one cell. If these are firing a high frequency, 100 hertz, when the other ones are coming in at slow time modulated 10 hertz, then exactly the same structure, but the system will have adapted to presumably compute the different types and forms of information that's coming in. I don't know. We have to look into this. But you can have, and in terms of saying same, I mean, look at Adam Hantman's work showing where all the inputs are coming in. I don't think it's the same. Same simply as in there's mossy fibers coming to the granule cell there, there's 4 of them, but to say that it's the same.
Actually, if I remember correctly, I think also the distribution of cells across the granule layer is not the same across different levels in the.
And there's added complexity as well as we are, and again, I always highlight the caveat so you're aware of them. We are randomly recording from granule cells anywhere between 400 and 800 microns under the surface. But there's been ideas out there that actually, as you go up the granule cell layer, the parallel fibers synapse with different places on the Purkinje cell. So then if you take a cohort of cells that are deep, maybe they're conveying a specific modality of information, or at least, and they synapse with more proximal because they need to be more important, whereas if you go higher up, more superficial in the granule cell layer, different modalities might go to the distal dendrites. So there's a whole level of organization that we're not completely clear of there either. So, but as far as specimen, it's the first time that we've gone in and really dissected the 3 different types of
so the story is that
Not the break response, you mean?
yeah, analytic break.
So it kind of you release the sodium channels from inside the
Yeah, exactly.
then you get the spike on the. Yeah, you can do that. I don't think it's like a very pronounced activation.
That way at laser.
But then you get better precision, presumably. Because if you're allowing the system to be in a situation that excitation will drive it because you haven't inactivated the sodium channels, presumably that already spikes. So if you kick it enough, I mean,
I think that would explain the fact that you get roughly the same number of spikes because so when the excitation comes in, you sort of reset the state of the sodium channels, right? So then the excitation comes in, boom, 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 boom. Whereas in the other case, there's probably variability depending on the history.
you're minus 60, is it in the inactivation of sodium channels when it's firing at 0.5 hertz under spontaneous? Maybe. It's definitely possible. I can't discount the fact that that could be the mechanism. Interesting.
Okay, thank you, Ian. I just wanted to I just wanted to note that I did upload the paper for the discussion next week. It's a bit different than the one that we used to have. It's a review paper on the spinal cord. So please read it. And yes, I think it's Tuesday when we have the right, and then we have another motor-focused discussion, and then we have the cerebellum papers the week after that. So I will try to upload before the weekend the cerebellum papers for the people who are presenting them as well. I think that's it. So.
Hi.
Hi.
How are you?
Hi. You are welcome for another
Yes.
He said that you
Okay.
If you want, I can break it.
Water would be good. Two down, one to go. Two down, one to go.
Did you read it? Your essay about you what? Yeah. Yeah, I guess
Exhausted?
Yeah. Just said two down, still one to go.
בין 2 ל-5, זה מה שיש לו.
לא, כי הוא צריך להיות באיזשהו משהו בצהריים.
אוקיי.
הוא שאל אם, כי דיברתי, already talked with Ian, I asked him whether it would be time to look into the fact that it would be time for you.
אין בעיה, אנחנו עכשיו, נראה לי שנרד לחנוכת בית של ענבל.
כן, בכלל.
בן רוצה לדבר איתו, טלי רוצה לדבר איתו.
Basically, what Mickey is doing here is basically, okay, I won't say the words what he's doing here, but you're being sold out to...
Yeah, shafted is the word.
I mean, basically, Ben wanted to talk to you. Vitaly wanted briefly to show you something, and I think you wanted to talk with Vadim Mizrahi. Which
Yeah, it's fine.
If there's someone, I don't know what his schedule is.
Yeah, it's fine.
So maybe I'll leave you with them. Actually, I don't know. We have like a housewarming for a lab of Inbal Goshen. I don't know if you want to join that. It's just kind of I don't know. Maybe you can talk to him. Maybe Ben. Maybe